like to welcome Michael Pilquist talking about FS3.
Thank you. Okay, so I'm happy to be here to talk about something I've been working on for the last 6 months, 9 months, you know, and sort of in spare time. I work on a project called FS2. We've seen a bunch of examples this morning and yesterday of that project. And you know, really what I want to look at is sort of where FS2 fits in the overall type-level ecosystem now, and sort of where we might want to take it in the future. This name was not intended to be like super provocative, so when I say FS3, it's not going to be a complete rewrite of the API or anything. But nonetheless, I thought it would be interesting maybe to start with a look back. So 6 years ago at Northeast Scala, a library called Scala Z Stream was born. So Paul Chiasano presented this particular talk, Advanced Stream Processing. It came out of the work he had done in the Red Book, one of those later chapters, right towards the end of the Red Book. And he sort of packaged up those ideas and released this library at this conference. 6 years is a long time, okay? At least in the Scala ecosystem. Contrary to maybe what John just said, that he said the Scala ecosystem moves slowly. I'd say we move very fast. Things change quite a bit. So 6 years ago, to give you an idea, the keynote at this conference extolled the virtues of the cake pattern. Okay? Things have changed. But nonetheless, so Paul said, stream processing is crying out for a simple and usable solution. This is an advanced talk on the design space for modular compositional stream processors. We want to create a library that has declarative stream processing that's powerful and comprehensible. Okay, so that was sort of the goal of this initial version of the library. Now 3 years passed. Things changed. We learned some things. We learned, what was useful, maybe what didn't work so well, what was too expressive. And in NE Scala 2016, the last time we were in Philadelphia, Runar Bjarnason gave a talk. I happened to be sick that day. I was at the Type Level Summit. I couldn't make this one, so I was sitting there in my pajamas watching it live streamed from my home office. We had just recently renamed the project from Scala Z Stream to FS2. Runar even says that here in his abstract. And he says that Scala Z Stream FS2 is a library that lets us write compositional, modular, safe, and efficient stream programs. Okay, so that's quite a bit of a challenge. And like I said, we learned some things. We changed the API a bit. Actually, it was in this talk that Runar presented the process 1 data type. If anybody remembers process 1, it was like the stream transducer that let us sort of like pull stuff from upstream and maybe emit some stuff that's different downstream. And Runar said, this really should be called a pipe, because that's really intuitively what this thing is. Okay, I went off and created a pull request to rename process 1 to pipe. And that brings us to today. So, here, the third time Northeast Scala is in Philadelphia, I wanted to talk about FS2 1.0, and we'll actually spend most of our time today talking about the current release that you can use right now, and really sort of like the way in which it sits at, a low level in this functional flux capacitor, if you will, of the type level ecosystem. So FS2 1.0 is built on CATS and CATS effect. And it powers pretty important infrastructure. So here we have Doobie and HTTP4S. There's a bunch of other projects as well. It sort of fits in at a very low level and provides a lot of infrastructure support to other folks. So if you kind of take a summary of the things that like Paul and Runar were talking about over the last 6 years, I wanted to add to that foundational. Right? This library not only needs to be comprehensible and compositional and so forth, but it also ends up being foundational. And when we sort of set out with that, at least as a goal and a metric to sort of cast any changes we want to make to the library in, it maybe changes the way in which we evolve the library. Right? We have to take it very seriously, the fact that like a slightly better API or a slightly more compositional API in this way might cause us to give on some of the other design constraints, the other goals, in ways that sort of ripple downstream through the entire ecosystem. Okay, so I wanted to give an idea for some of the things that make FS2's API a little different than like a normal stream library. And so I call this part the control flow safari. We're going to take a tour through various stream programs written in the FS2 1.0 API that maybe aren't so straightforward to do in other applications. All right, so this first one is this metered combinator. The metered combinator is a method on stream. So stream, just in case you haven't seen it, it can evaluate effects of some type F and can output 0 or more values of some type O. Okay? And what this metered function does is says, given some timer, something that can sort of manage time in our effect F, and given some rate, let's say 5 seconds, sort of pair up stuff coming from our source stream with the individual events coming from some constructor, some stream that gets created that emits a value every 5 seconds, sort of pair them up and in effect slow down the output. Right? So we started with a stream FO, we end with a stream FO, but in the process we've sort of paired up each individual element with a timer event, if you will. Right? So we've slowed down and metered that output out nice and slow. And so the interesting thing I think about this particular combinator is the implementation and the way in which it's expressed. We construct this stream using this fixed rate constructor. Right? So you can imagine this stream like emits like a timestamp every 5 seconds. And then we just zip it with our source stream. Okay? And so you can imagine, like, you can sort of kind of guess how stream zip works, right? You've got two streams, you kind of want to line up their elements side by side and just kind of bring them together. Right? So if I've got one stream that's only outputting an event every 5 seconds, when you zip those together, the net effect is that we slow down that original source stream. In this case, we're throwing away the actual values, the timestamps coming out via the zip right combinator. But you could imagine this as like a zip as well with just like a map tacked on, right? So a little bit different than what you might think of as like, an iterator in a functional style. All right, here's another one. This is very common. You'll see this pattern quite a bit in systems written with FS2. The general idea here is we have a concurrent lock-free data structure representing like a first in, first out queue. It's a bounded queue though, so it can only have up to like, some parameterized number of elements in it. And if we enqueue a bunch of elements and we hit that max, then any additional enqueue effects are going to semantically block. For the folks that were here yesterday, Fabio taught us all about semantic blocking, right? And so it'll block in sort of a safe way. We're not going to actually hold up a operating system thread or any other type of expensive resource, but nonetheless, we can sort of program as if we were. All right, so anyway, in this particular case, we create one of these bounded queues. We create a producer and a consumer. The producer has like some source stream that it's just going to feed into the queue via the source through queue.enqueue. And then we'll have a consumer which just dequeues elements from the queue. And then we have this interesting combinator called concurrently, which sort of lets us like say, let's return the consumer stream. But as folks sort of pull on that consumer stream and get elements out of it, we're going to be running this producer stream in the background. And if the consumer stream terminates, we want to sort of shut down that producer stream concurrently in the background. Right? This is all purely functional, of course, so nothing's actually happening. We're building up descriptions of stream programs here. But that's sort of the intuition. In fact, if we sort of take that and kind of beef it up a bit, go from like maybe a naive implementation to something that sort of preserves high performance. If we have like really chunky streams, you can imagine like streaming like big files from disk or something, or big files from AWS. If we kind of want to preserve some of those properties and maybe have some other like different shutdown properties, we end up with this other built-in combinator called prefetch-n. The idea behind prefetch-n is that like we want to have a stream that will allow so many elements to sort of be fetched ahead of time and put into this queue internally while downstream processes elements. Right? Something we used to hear a lot with Scala Z Stream and earlier versions of FS2 was is there any type of back pressure? FS2 being a pool-based model, back pressure is inherent in its design, but you can do things like this to sort of introduce concurrency and sort of kind of get the best of both worlds. All right, one more example in our control flow stuff. This is an interesting case. This is sort of a newer API for folks that have only used FS2 0.10 or before. You haven't seen this. I'll run through this one pretty quick. The idea here is we're going to have some source stream, and then we're going to create an infinite stream sort of workers, if you will. An infinite stream where each entry in this infinite stream is another stream of elements. Okay? And for however many of these inner streams we create, each one of them will get an even number of elements from the source stream, sort of balanced across them. So you can sort of think of this as like round robining, right? If I take, in this case, take num workers, if I take 10 from this balanced stream, what I end up with is 10 substreams that each sort of get, you know, a window on the original stream itself. Okay? So I have a stream of streams. I take a certain number of workers through it. Each worker I configure to do some work by using just normal stream APIs. And then I sort of run it all in parallel and compile it down to an I/O effect. Right? And so my whole program in this case just has a value of I/O of unit because the output of my program is less important than the effects that it's actually running. Okay, so I know that one's kind of mind-bending, but that's the type of thing we want to be able to do with the FS2 API. All right, let's talk about stream compilation. So when I said, you know, on the last slide I had that compile.drain, the notion of stream compilation is a transformation from the streamy world to a single value in the effect world. So I characterize this here with like the conversions from stream of FO to some G of R, where like F and G typically are the same, right? But not always, right? Some stream FOs might get compiled to unexpected Gs, and I'll talk about that in a moment. All right, so this notion of getting out of the stream world typically happens at the very end of the program. Like a lot of the same metrics you would use for like when do you get out of I/O, you might want to use when thinking about like how to get out of a stream-based program. Okay. Here's common types of compilation. We won't look at all of these in detail, but like notice the very first stream type we're going to look at. It's called pure streams. We actually have an effect called pure. A pure stream is something that cannot evaluate effects. It's just built up with like simple values and simple constructors. So when our effect type is pure, if we said like compile it to a list, what we get back is not a pure list of O, but rather just a list of O, right? So our G sort of evaporated, right? Or if you're familiar with like the ID effect, you can sort of think about G being the ID effect in this case. Okay. So anyway, so if we have pure streams, we can operate sort of in this pure world completely outside of any type of effectful processing, and we have all of these sort of rich combinators, right? We can convert to any collection in a pure way. So like anytime you need to like write some complicated unfold, like lazy list type sequencing thing, you can use FS2 for it, and it's almost always going to be a better choice API-wise. Okay? We have like efficient conversions of like an infinite stream of strings, or at least potentially infinite stream of strings that can sort of be efficiently converted to a string as long as it eventually terminates. And various other combinators for doing, for getting out of the stream world back into the pure world. This same API works for effectful stuff as well, right? So if we have just like a stream of FO for some arbitrary effect, or we have like a stream of IO, O, right? When we compile those streams, we get back the same types, but sort of wrapped in our effect type, right? So like calling compile.toList on a stream FO, we get back an F of list O, all right? So in this particular case, like F and G are the same, right? And this is typically what we work with. And in fact, it's the very same API, the very same compilation API works across all of these. Like if any method that works on a pure stream will work on an effectful stream. And there's some other types of streams that we won't talk about today, or at least just not right now, maybe in a little bit. But nonetheless, like compilation sort of always works the same. Compilation sort of works like this. We have this compiler trait. You don't often see this. This is sort of an advanced thing. We've got this compiler trait. And it sort of characterizes the way in which the library actually does the conversion. If you kind of look carefully, you can see that like the first parameter to this apply method is a stream FO, and it gives us back a G of R. And everything that's left sort of looks like a fold, right? We've got some initial value. It's in a thunk for some weird reason, right? But there's some initial value. There's some accumulator function, but like instead of accumulating individual elements, we're accumulating chunks, like strict chunks of elements, sort of like lists. We've got some weird finalize that like you'd think would just be like a map on the end of our program, but in this case has to be put off to the side. Okay, so this is how stream compilation actually functions in FS2 1.0. And for the various stream types we saw in the previous slides, there's just various different compilers that can be constructed, that are all available implicitly, that can be, sort of plugged in to get those proper conversions. Okay, one other note about FS2 1.0, that's that stream and pull don't really exist. Stream and pull are just new types on this more fundamental data type. Our fundamental data type is really a stream algebra in a free-ish monad. Okay? So what we have here on the left, we actually have the stream and pull. Like they're literally any classes or any vals, right? Classes that just wrap this value of free C. Streams themselves, the final parameter here in our free monad is a unit, whereas pulls, the only difference is that pulls can have any arbitrary type there. So you can imagine like every pull can be expressed as a stream, but not vice. Sorry, I said the backwards. Every stream can be expressed as a pull, but not every pull can be expressed as a stream. And then I said it's sort of like a free-ish monad because our free structure has some additional constructors. Notably here we have this fail constructor. So we have like a free monad that can raise errors. We have this strange sort of interrupted constructor, which lets us sort of interrupt execution as it's occurring and sort of jump out to a good spot. And then we have this bind constructor. You might think that's like a normal flat map bind. But rather than being like a function from like R to a free, it's really a function from like either an error that was raised or a value R to a new free structure. So it's sort of like an error aware bind. Okay? And then we have like our actual stream algebra, maybe nicely modular, separate from actual sequencing of our operations. Our stream algebra provides some constructions at the top that maybe feel familiar, like we got to be able to output some elements, we got to be able to step streams forward perhaps. But we have these like final four, the bottom four there are all related to like scope and resource management. I'm going to talk more about that in a moment. Okay. So if we're looking at FS3, the question becomes, well, like, what's wrong with 1.0? What are we looking to address with a new API? And I'd say there's really two things. I'm going to talk mostly about the second one. But the first is that effect types have changed a bunch. When Paul stood on the stage in 2013, really the only effect type people used with streams was Scala Z's concurrent task. For folks that have used Scala Z's concurrent task, it shows its age, right? It's a bit dated. There's a lot of things that we've learned over the last 6 years. Furthermore, there are our libraries like Cat's Effect have matured over the past 2 years to provide all sorts of more interesting functionality. And sort of the question here is that like, FS2 evolved along with those libraries, but if we took like a deeper look, not just API stuff, what could we do sort of internally to maybe take advantage of things like bracketing and things like cancellation in a more first-class way? The other thing though is just that like the interpreter for this stuff is actually kind of complex. For various technical reasons, it becomes very difficult to look through like really how FS2 is able to kind of do what it does and do it in a performant way. I would say it's much more complex than like just a normal sort of free-based algebra. Okay. So if those are our goals, I think equally important, these are the things I'm not willing to give up on, right? Because maybe with just one or two concessions here to this bottom list, if we gave up on those things, we might be able to get a lot of gains in some of the others. All right, so I'm going to look at each of these in detail. First is that FS2 fundamentally is polymorphic in the effect type. We're not going to ever hard code to I/O, right? These are all examples on the right, all examples of common effect types people put into streams. The first four are just from the library itself. Right? All four of those show up quite a bit. That stream fallible is kind of interesting, by the way. It's a pure stream which can raise errors. So when we compile, we actually get either's out, right? Either the error that occurred or like whatever the result was of compilation. For folks that have used Doobie, you've probably seen stream of connection I/O. right? Connection IO is like a free monad, right? So now we have like sort of like free and free, if you will. And then like, I listed these last two on the bottom here, stream task and stream UIO, and some others. Because like often when people think like, oh, we're polymorphic in effect type, we think that the point is writing code that can sort of abstract over effect libraries. And that's nice, but that's not why I care about it, okay? So I'd say of all of those examples, those last two are like the least important to me personally. All right, I want a single API for pure and effectful streams, right? So by being polymorphic in effect type, that's great. But all of my API functions, all my built-in combinators, I want to be able to express stream programs regardless of what effect type I happen to be using. So in this case, I just have like two examples, doing some string interspersing and then compiling it down. But furthermore, I want to be able to write this code in a way where I can abstract over this stuff in a first-class way. We saw that compiler trait. We can write that same program, in this case, taking like a compiler implicitly, and be able to express that particular operation once. I would say one of the most distinguishing things about the FS2 API is the recursive pull data type, right? So pulls are basically streams, but that finish with a result of type R. Okay, so the idea is like you might evaluate some effects, you might emit some values, but then you eventually finish with an R, exactly one R, right? And so we sort of have this API that lets you kind of step streams incrementally in a purely referentially transparent way, and write really powerful stream combinators just using like regular tail recursive monadic functions. Like what this one particular one does isn't really that important. Just the idea that I can sort of do the equivalent of like an Aquastream graph stage, for example, but with a purely functional API, something that's more comprehensible than the mutability of something like a graph stage. This one's a little bit harder to motivate without another half an hour, but stream bracketing, stream resource management becomes really important. Stream resource management fundamentally is different than bracketing resources in I/O, right, or in a value-based effect type. Unlike things like I/O, or unlike the bracket of type class, in FS2, if you flat map over a stream that has a resource allocated, that extends the lifetime of those resources. Okay? So this is like fundamentally at odds with the definition of the bracket type class from Cat's effect. A stream cannot have an instance of bracket. And then finally, I want to continue to support all these different control flow things we saw. Here was just another example. This is kind of a weird one. I'm going to run some stream S, but after 10 seconds, I'm going to interrupt it if it hasn't finished, and then resume with S2, right? And that's just like regular old stream, concat, right? So like you can imagine, like stream interruption isn't really a direct mapping onto effect cancellation, right? Because if we just compiled our whole program to like one effect and just cancel that effect, we kind of break out of it completely. And here we kind of have like this notion of like a boundary almost, right? Like some resumption boundary. For the folks here yesterday, Adam Rosine talked about this reified approach to creating a stream program as an example. So that's sort of what we did. Start with like the API we want. Like we have this pull type, FO and R. We want to be able to compile it down to, in this case, we were going to compile it down to an effectful value who has some output type S. And then if we reach the natural end of the stream, whatever result value it finished with, right? Like we saw earlier, our compiler from 1.0 was sort of like a chunky fold. So like let's just express the chunky fold here, right? We have some initial value and we have an accumulator that folds chunks together. And so the question is like, how far can we take this? Well, if you look at the FS2 code, you might know this already, but we love variance annotations. And everybody should, right? Because when you use variance annotations, despite the complexity they add, we get much, much, much better type inference, right? And in fact, in the few places in the FS2 code base where we actually said like, the variance is getting too difficult, we're just going to make everything invariant and then just cast the few times we have to, we have found bugs, right, where we were not smarter than the compiler. So anyway, so we use variance annotation. So the first thing we want to do is add all those variance annotations here, and then sort of use our normal set of tricks to like make everything compile again. In this particular case, I had a bunch of parameters that were in like contravariant position. The compiler yells, and we go and we add additional type bounds to our function. And like, it starts okay, right? We want to create like this pure operation for polls. So we have like this def pure, we put it in the companion object. We kind of have to figure out like what type do we want to return. Well, like a pure value R just represents a stream that evaluates no effects, outputs no values, and then just finishes with that R, right? It's our unit for our pull monad. So our effect type in this case is F. Our output type is nothing. Like, why don't we have both of those set to nothing? It's because inference is better this way, unfortunately. But our result type is R. And then actually implementing this is fairly straightforward, right? When compile is called, all we need to do is take our initial state we were passed and take our R and put it in a sum, lift all of that into our effect, right? Fairly straightforward. And similarly, all of sort of the main data constructors all work out relatively easily. Outputting chunks is relatively easy. In this case, you can see like the result type of this pull is now a unit, right? Because it's going to output some things, then we're done, right? So our result is a unit. Evaluating effects is pretty easy. We can lift an f of r into a pull f nothing r, right? Because when we get compiled, all we have to do is sort of map over that f of r and kind of change the shape a little bit, use the values we have to sort of make it work. And then we run into this case. So this is the pull equivalent of like the bracket API, right? The idea here is that we've got some resource f of r, and we've got some finalizer or some release function that says, given an acquired r, release it, right? So maybe I'm going to acquire a socket, and then later I want to close the socket and return it to the operating system. And because of the fundamental difference here between effect bracketing and stream bracketing, there's really not much we can do. Like, we have a sync instance for our f type, but that bracket case that it provides doesn't really solve anything for us. And so we adjust. And this is representative of what you'll see right now on the topic FS3 branch. The general idea here is that, well, compile wasn't really the right starting point, right? We sort of took it as far as we could. It ended up not being the starting point for this particular API. And instead, the key abstract method that each pull constructor is going to have to implement is this step thing. And this step thing is going to sort of deal with the difference in bracketing by introducing this notion of scopes. Okay? And so scopes are basically a multi-way tree. Every individual scope has a list of acquired resources and the associated finalizers with them. You can imagine if you close a tree node, all of those resources are released. But then since it's a multi-way tree, right, it also has a set of child scopes, and like closing a node in the tree sort of closes the whole subtree. With that, and with some slight adjustments here, we can sort of implement the desired semantics around stream level and pull level bracketing. That gives us this. So now in FS3, we have stream is still a new type for pull, right? Stream's just an anyval wrapper around pull. Pull itself has a lot more constructors. And that maybe intuitively makes sense because this is less modular than what we had in 1.0, right? We now have to do all of the interruption handling, all of the error handling, and all of the sequencing that the free monad provided us. But we also have to do all the stream stuff, right? All into one type. I don't know if like that loss of modularity is important or not. I tend to think that the resulting code here is much more approachable, but that remains to be seen. Okay. All right. So I'm really close to having this all working. I said there's 2.5% left to get it there. I measured that by running my test suite against it and looking at how many tests I cannot get to pass. But just to give you an idea, this is the FS2 1.0 test suite run against this new implementation. We're down to 20 tests out of about 800. Unfortunately, as our colleague Pavel says, getting interruption to work is very difficult. In the FS2 1.0 case, it took us a long time to get that interruption stuff to work. And sometimes getting those last couple tests passing might cause us to like fundamentally rethink some of the approaches we're taking. With that said, even if this goes nowhere, there's been a bunch of neat things that have come out of it. I call these our space program effects. There are things that we're benefiting from even if we don't ourselves ever go to the moon. So the first is dead code elimination and simplified scope management. Basically, if you use FS2 1.0.4, you're already benefiting from this. There are cool things that we noticed sort of when doing this work that we were able to simplify and unify various ways that resources get released to be a little bit more predictable. The second is like interesting API findings. So does anybody use like warn value discard, the compiler option? Or anybody uses like Rob's compiler options, right? Basically like tell me when I throw away a value. Well, like we use that flag, but we had like the monadic equivalent of it. Like we provided this way to go from a pull to a stream, but we didn't tell you we were throwing away the R, right? So that's like literally the only API change in FS3 as of right now is making that a compiler error, right? If you want that, you just say void, right? Like p.void.stream. And then finally, we have a new test suite. Basically, take all of the 6 years of accreted, test cases that we found, and put them into a new structure that's much more approachable. Just a quick example of this. Don't have to look at it, but the key point here is that we have a Scala check generator that is doing an effectful asynchronous computation and is not blocking a thread. That is not possible with Scala check. That is possible with the new Scala test 3.2 generator support. All right, just wrapping up. Like I said, I don't know where this is going to go. We might find pieces of it useful. We might abandon the branch. I think a lot of that's going to depend on how we get those last 20 tests passing. If you're interested, please come along, talk to us either in Gitter or on GitHub. And more generally, I just wanted to mention that like we should be okay with experimenting. John just talked about that in his talk on Fury. Experimenting is fun. We learn things from it, even if we don't necessarily directly use the outputs of it. At the same time, there's a bunch of things we learn in the development of mature software, and hence I think we should celebrate that maturity and not always just look for like the simplest, newest library, right? Sometimes we should be aware of those differences. Anyway, that's all I had. Thanks so much for your time.